Hello guys and welcome to another USACO problem. Today we're going to do something different. I'm going to attempt to live solve a problem, which just means that I have not read the problem beforehand and also analyzed the solution. I'm doing it on the spot right here. So I'm a little bit nervous for this one, but we'll see how long it takes me to do this. So let's do the 2023 December contest silver problem 1, Bovine Acrobatics. So Farmer John has decided to make his cows do some acrobatics. First, Farmer John weighs his cows and finds that they have n distinct weights. Okay. In particular, for each I in 1 to n, AI of his cows have a weight of WI. Okay, and his most popular stunt involves the cows forming balanced towers. A tower is a sequence of cows where each cow is stacked on top of the next, and a tower is balanced if every cow with a cow directly above it has weight at least K. Huh. So, okay, so we have a tower, and it's only balanced if every cow with a cow directly above it has weight at least K. Okay, and K is a constant. At least K greater than the weight of the cow directly above it. Okay, that makes more sense. Okay. Any cow can be part of at most one balanced tower. So a cow cannot be at two at the same time. And he wants to create at most M balanced towers of cows, and at most how many cows can be part of some tower. Alright, so we do have a limit on how many towers we can make, but it wants the most cows in the towers, I guess. Okay, so I've just hopped on my whiteboard and I have created the input case that's shown right over here. And for this one, our n is 3, and I forgot what n is. N is n distinct weights. Okay, so that's basically how many lines we're supposed to read in. And then M is the next one, and M is at most how many balanced towers, and then K, which is every cow has to be K, at least K greater than the cow under it. And then we have the WI and AI, which just means that we have 4 cows of weight 9, and we have 6 cows of weight 7. So in total we have about 15 cows, but it's not gonna show you each cow like on its own line. It's gonna put the cows with the same weights together. Okay. Alright, so we have this many cows, but how many towers can we create? I actually don't know for at this spot here. So K is 2, so that means every cow on top of a tower has to be at least 2 more than the cow under it. So I guess if our weights are 5, 7, 9, we can stack those, right? So I think the most efficient here would be just stacking 5, 7, 9. This will make us 1 tower, and we need 5 of them. And in this case, at most we can make 4 towers, but then we can make a partial tower. So basically so if we make 4 towers right here, let's make 4 towers. Okay, so we have made 4 towers, then we run out of 9s because the total amount of 9s is just 4. So we run out of 9s, but we still have 1 5 and 2 7s. So we can make one more tower using that. So let's do that. Okay, so now we have 5 towers. This is gonna be 5 over here. So all of this is 5 towers, and that's the maximum we can make. So if we look at this, that's 3 times 5 is 15. So there's 14 cows that are actually on a tower. So let's see. Okay, yes, Yes, we have 14 cows that can be placed on a tower. Alright. Okay, this is actually an interesting problem. So obviously, first of all, we have to sort the weights. But after we sort the weights, how do we make the tower though? Okay. So this example is a little bit basic. Let's quickly move on to the next one. I think there's one more. Yep. So let's move on to this one. Okay, so this is our next example. If I wrote that correctly. Yep. So basically for this one, now our M, which means how many towers, is still 5, but our K has been increased to 3. So we have to make stacks, but each of them has to be like 3 distance away, each of the weights. So if we have weight 5, we have weight 7, we have weight 9, very similar. But now we cannot stack like 5, 7, 9, because that would only be 2. So this only has 2 difference, and this only has 2 difference. And we have to have at least 3 difference to be able to stack something. So we can't do that. So the only thing I guess we can do is 5, 9. And so in this case, you have 5 towers. So yeah, I guess you just use the 5. You just use the 4. Okay, so you only have 4, 9. So you can only do 4 towers of 5, 9. So 5, 9, 9, 5, 9, 5, 5, 9. And then after this, you run out of 9s, but you still have 5s. Okay, but you can't stack 5 with 7. So you can either have this as 5 or this as 7. So if you have another 5, then yeah. So how many cows is that? That is like 9. 9. Okay. Okay. Okay, I guess in this problem you have many choices. Okay, so this test case is also a pretty basic one. So I don't really like these test cases. Let's create our own actually, because this test case is basic. Okay, let's create a test case. So we don't have to have 3 of them, but we can do 5 towers, and we can do 3 difference. So let's say the smallest weight is 1, and we have like 3 of them. Then let's say we have like a 2, and then we have like I don't know, 5 of them. Then let's have like a 4, then we have 7 of them. Then we have, let's say, what did it say? I'm gonna say like 5. 5, we have like 2 of them, only 2 5s. And then 6. And then 9. Okay. 6, we have 1 of them. 9, we have like, I don't know, 5 of them. Okay. So n doesn't really matter, but I'll write it anyways, so it's n equals 6. But right now we have a bunch of stuff. And we have to make towers. We have to make 5 towers with distance of 3. So if you have distance of 3, let's see. So you can, I guess if you choose the first one, then you can also choose the distance of 3, so that's 4. And then you add 3 more, and that's like 7. So 7 means like anything above 4 is also okay. Above 7, I mean. So then you can have 1, 4, and 9 form a tower. But would you want that to form a tower? So it's, you can have everything. So obviously if you want to stack 1s, you cannot stack 2. You have to stack at least a 4. But would you want to just stack 1 with 9 though? Or would you want to just have 4? Because I think having 4, yeah, I think having 4 is you have to have it. I mean it's just better to have 4. Well, even though you're using the 4, if someone else is using it, it's the same result. You get the same result at the end. So I think it's beneficial to have 4. So we can have 4 right here. Then we have 9 right here. And that is a 3 stack. And I think 3 stack is the best you can do here. You start with you start with you start with this. You start with the smallest and then you go up. And I think a three stack, that's the biggest stack you can do. Because if you go up from a 2, can you do a better one? 2. You cannot do a better one. Yeah, 2, you cannot do a better one. You cannot do a stack with like 4. The biggest stack has to be starting at 1. Okay. So, okay. We have the stack. Let's take it. Let's take it. So to take it, I guess let's just take all of it, right? Let's just take 1, 4, and 9. We're gonna take the minimum of 1, 4, and 9. So the minimum supply is gonna be 3. So we can have 3 towers. So we can have 1, 4, 9, 1, 4, 9, and 1, 4, 9. Okay. So now after this, 1 and 3, we don't have any supply of anymore. And then 4, because we subtracted 3, so this is going to be 7 minus 3, which is 4. And then 9, we subtract 3, and 5 minus 3 is 2. Okay, so now we have... Okay, so I guess now some supplies have been used up. Can we repeat this process? Can we repeat this process and do the same thing? Starting at 2, let's make a tower with the smallest being 2 because our smallest already gone. So let's start from 2. Okay, I guess from 2, let's go up 3, so that's at least 5 right here. And then 5, let's go up 3, and that's 8. But we don't have an 8, so the closest thing to 8 we have is 9. Okay, so that's the biggest stack you can do, and again, it's a 3 stack. And in this case, okay, so we have 2, 2, and 5. So the best you can do is 2, and that basically solves our problem. Let's make M a little bit bigger. Let's make it 7 actually. So we have to make it 7, but we're doing the same thing, right? This is still a 3 stack, and you can stack 2 because that's the most you can do. That's the most supply for 9 and 5. So let's stack 2. 2, 5, and 9. 2, 5, and 9. Okay. Hope I'm not doing something wrong here. But I think this is right. So now we don't have 5 and 2. Now we don't have this. And we need to subtract 2, giving us 3 here. Awesome. Okay. So right now our smallest is still the 2. Okay, so now our smallest is still the 2. It goes up 3 and you can't do 4, so that's 6. You can do one more, and then you can do your one more, and then you can keep your... Okay, so there's a kind of like a solution right there. I'm not sure if it's the most time efficient, but we do have a lot of distinct weights. We do have a ton of distinct weights. So we can't necessarily... Yeah, we can have like 10 to the 9th power of balanced towers of cows. And if we just do this algorithm, just like go to the next one, that's gonna time out. That's like, because M can go up to 10 to the 9. Like that's a lot of towers though. So how do we make this algorithm more efficient, like stacking? Okay, so I've like thought about this for a while, and I think we should like somehow do all the stacks at once. Like don't do it like separately. So say I want to stack from 1 and then I go to 5 and then go to 9. That is just doing one type of stack, and if your AI is very low for that stack, then you don't really get much out of it, because then you'd have to do a lot of these kind of stacks. And I think we should do these kind of stacks with other stacks actually. So let me just erase some stuff, and let's do it in another way where we can make... So okay, so we have seven stacks that we want to make. 7 stacks. Right now we're looking at the first row here, and we're just seeing 3 of them. Okay, let's record that. Okay, let's over here, let's say, okay, our new WI and AI. So we need 7. We only have 3. We need more stacks on the bottom. So in this case right here, we're gonna look at this, and then we're like okay, we only have 3. We need more. So we're gonna store this over here, store this right here, and then we're gonna just move on to the next one. We're gonna move on to the next one. And that, just as a visual here, I'm gonna show you guys what I mean. So I'm just putting 3 ones down, but we still have a lot of space left. So okay, so now we're looking at this one over here. Then we're like, okay, well, can it stack on 1? It can't really, right? It can't really stack on 1 because the k is 3. So why not we make them bases too? So in this case, if we add, there's 5 of them, and we only have 7 bases, we only have 3. So we can't take all of the 5, because that will make it 8. So we can only take 4 of the 5. So we're gonna make this 1 right over here. So we take 4 of the 5, we fill up all of our stacks. So we're taking this, but we're not stacking it on top. Instead, we're actually putting it on the side here. So 2, 2, 2, 2. We still have one more 2 left over. And that for that 1, 2, we can't really do anything because we can't really stack it. So we'll just leave it like that. And in here, we're going to record. Let's say we have, okay, so this is like bases. For like the base, we're going to have 2, and then we're going to have 4 of them. Okay, let's look at this. So 4, 7. The most smallest weighted base that we have right now is 1. And if you give me a 4, hey, I can stack it on 1 because 1 plus 3 is going to be equal to 4. So let's stack it on 1. And we want to stack as many as possible because it's kind of like a greedy solution over here. So we have 7 of them, but we only have 3 ones. Okay, so let's stack 3 then. Okay, so we're gonna stack 3 of them. So we're gonna destroy this 7 over here. We're gonna make it 4 because we've just subtracted 3, and we're gonna put it onto the ones over here. So 4, 4, and 4. But now our ones just turned into 4s. So all of our ones gets turned into 4s. And you can see now, this is not the smallest anymore. Right now, we can't really stack much on here, but right now we can stack a lot of stuff on here because this one is smaller. So let's put that on top of this one. So we have, right now, on top, we have 3 4s and 4 2s. Awesome. Now we just check, okay, so we put it on 1, let's try to put it on 2. And you realize that you can't really put 4 on 2 because the k is 3. So you're like, okay, I cannot do anything with the 4 left over. Let's look at the next one. 5. Well, 5 right now, we can put on 2 actually. And we have 2 of them. Awesome. Let's put them all on 2s. So right now, we can see that this is our smallest one. And we have 4 of them. But 5, we only have 2 of them. We're going to completely wipe out 5 right here. We're going to completely wipe out 5. And we're going to only put a partial amount to the 2s over here. So we're going to put 2 of them specifically. So we're going to put a 5 here. We're going to put a 5 here. Now you realize that 2 of the 2s just became 5s. So instead of 4 here, we're gonna wipe it out. It's not a 4 anymore. It's a 2. And for the weights here, we're going to add another 5 here. So we can add it just to the bottom. So 5, we have 2 of them. Okay, let's look at the next one. We have 6. We have 6. We have 1 6. Can we stack the 6? Well, we can stack 6 actually, and let's just try to stack it on the smallest one right here. So we have 2 of 2, and we have only 1 of 6, so let's stack it right here, and this becomes 0. Okay, let's look at the next one. We have a 9. We have a 9. That's pretty big. I think we can stack it on a lot of things over here. And just to make it more complicated, let's make it a 7. So we have 7 9s, and we're like, okay, we can stack a lot of it, right? So for the 9 here, let's try to stack it on the smallest one, which is 2. Yes, we can stack it, and we only have 2, so we're gonna stack all of them. So I guess we're gonna change this one to, instead of 7, it's gonna be 5, and we're gonna stack 2 of them on. Oh wait, what? Did I forget to minus 1 over here? Well, I'm looking at 1 here. Okay, I think I forgot to minus 1 here. So then let's just stack 1, okay? So let's stack the 7 over here. I meant 9, and we're gonna change it to 6. Okay, so now that we have stacked 1, we're gonna erase this one, and we're gonna make it 1 of 9 over here. But we're not done. We can still look at this one and we're like, okay, we can stack a 9 on a 4. So we're gonna do that. And we only have 3 here, so we're gonna stack all of it on these 4. So this 9, 9, 9. And then this 4 is gonna subtract this 3. It's gonna subtract that by 3, so there's 3 left. And now we don't have this anymore. We're gonna have 3 more 9s. So we're gonna guess we're just gonna add it. So 3 more 9s. It's 4. Okay, we can stack even more. We can stack even more. We can look at the 5 over here and we're like, okay, we can stack it on there. So let's just stack it on there. 9 over here, 9 over here. We stacked all of them. So this becomes a 1. Becomes a 1. And no more 5. 2. We're gonna have 9, 6. Wait, why did the 6 go? The 6 went away? Okay, something's happening with the 6. But anyways, I think we erased the 6 or something. Okay, I think we should. How many 9s are there? 7? Yeah, we can stack a 9 on here. Yeah, we erased the 6 somehow, and this becomes 7. Anyways, I did something wrong on that, but this should be like the general rule, I think. But I think this case is another one of those weird cases where it's like I don't think I got everything. But the general rule is that if it can be stacked, stack as many as possible, and then transform them to bases, right? So every time we're looking at a set of weights, we're trying to stack as many as possible to our current set right now. And we're also trying to make them the base. Kind of. Like stacking them on nothing. We can stack them on nothing or just like making them the base. And then when we have filled out all of our bases, we're just gonna keep on stacking. We're gonna keep on stacking everything to the smallest weight that we can possibly have. We're gonna stack as many as possible and keep going. And I really hope that this solution doesn't time out for this problem. Okay, let's try and write the code for this. You guys see the lighting is a bit different. It's because I just came back from a viola class, and during the whole class I was praying that this solution doesn't time out. So let's just code up and let's see it. So I'm actually nervous about this. Really don't know how this solution is gonna go. Okay, this one's gonna be, I think it was December one. I have also recently switched to using VS Code and Vim. Please don't mind me if I go super slow, because this is like, I'm still learning Vim, and honestly, I'm just like resisting myself from using the mouse. Okay, enough talk. Let's actually set up. So, okay, for the acrobatics.in, let's see. Which case do we want? I'm thinking the second case, maybe. Okay. Alright, so first thing, include this. Okay, now let's name our constant. So we have n, m, and k for our constant over here. Then basically to keep track, we just use a map. So I think we're good. So I'm just gonna say int main. So now let's read in the input. This acrobatics and reopen acrobatics. So now I'm pretty sure it's in this order. Okay, yes. So now that we've read in the constants, we gotta read in the actual map of the cow. So I think we would just achieve this by doing a map int, and let's just call this. What should we call it? So I just said cows. Yeah. So we have our cows. For like 0, I1, and I plus. And I think okay, so let's do int. So first one is gonna be W, and then the next one's gonna be A. So WA, singing WA. Then we're just gonna say cows W equals A. Cows W equals A. So we're mapping the weight to the A. That's great. And I think map sorts it by itself. Like sorted by the weight itself. Just to confirm that, I want to do a for loop. Just to make sure we got everything right. And let's click. Okay, finally, after ages of waiting, we finally get our result, and yes, it is in sorted order. Yeah. I'm also confused in like how does like adding it work? We're gonna have to test that. So if I just say cows 10, which is not a real thing, equals 2, will give it to us. Say not a real thing, like 4. While in the loop, will give it to us. We could just add after loop. Honestly, it doesn't matter. We could just add after loop because we're gonna use, because we would need to loop through and kind of like remove stuff. Okay, so we successfully added. However, we didn't add the. I don't know why we didn't add the 4, but we'll add it to the end. So I guess we can get rid of this. We can get rid of all these lines. So what do we need to do now? We need to actually start doing the thing, like cycling and trying to add stuff. So we need another map of the current state. So map int the current. And now we need to add the bases. So if we don't have enough bases, we need to add bases. Okay, so let's just say bases 0. And we're gonna cycle through I equals 0, I small and n. No. We're gonna cycle yeah, we're gonna cycle the list. So not key value WA and cows. Okay, now we're cycling the list. We have both W and A. I'm gonna say so if basis is already equal to the number of bases we need, which is m, then we don't need to do anything. But the more important thing is, if it's not, then we need to do something. Okay, let's close this. If the basis is not m, we need to add it to the basis. So we're gonna add a to basis, and we gotta hope that a doesn't exceed, or we could actually do. Let's see. Okay, so we need to split this into two. So if a plus basis is actually bigger than m, then we need to just set basis. We're gonna set it to M. Then we're gonna say a minus, no. We got a minus first, don't we? So we got a minus first. So a, we're gonna subtract by m minus basis. So m minus basis is how many we need from basis to m. And if we minus that, then we get to minus. And I think it's because it's a const. We'll just do this and just use a2 for now. a2 a2, and I don't think we have checked w yet. Yeah, okay. So yeah, now we're just checking bases, right? Basis a2 minus equals m minus basis, then we make basis equals m. Okay, that's great. Otherwise that means doesn't fill. So we just do basis plus equals a, and we don't want to do anything because we have used everything. We just add a common right here. And okay, now okay, so now we're gonna do what do we do? So that's adding bases. Now basically our logic is just going to be on adding, stacking. So now we just need to stack. But how do we actually stack? And go back to refer. When we get a weights and an A, we need to stack that on top of something. And we gotta first look at the smallest one. We gotta first look at this in the current right here. We gotta look at the smallest weights possible. And we're gonna try to stack as many of that to the smallest bases as we can. And if we can stack all of them, then we just completely remove it, right? And then we move on to the next one, and then we're trying to stack as many as we can. So every single time, we're just trying to stack as many as we can. Only if the current one is still 3 bigger than the current one we're looking. Oh wait, I forgot something. So adding basis, we also need to actually add it. We also need to actually add it to the current, because current is gonna be filled with bases. So we added that many bases. So m minus basis is the number of bases we add. So we're gonna say current, and it's weight first, so w2 I guess, equals m minus basis. That's gonna be how many ever base we add, and we already subtracted that from a2. For this, same. Current w2 equals a. We've added all of them. Stacking. We have to cycle through current, so 4, okay, I ran out of arguments. I guess we're gonna call it CW and CA, and a current. So okay, so we're gonna cycle through. We're gonna cycle through current, and we have the weights and we have the CA. So we're gonna say if. We're gonna check if we can actually stack to this, right? We're gonna check if we can. So if CW plus K is smaller than or equal to W2. So what does this mean? This just means CW is a smaller one, so CW plus K is gonna be the limit right there, and it has to be smaller or equal to W2. That we can stack. I think else then the others we can't really stack either. So oops. So else. Okay, so if we can stack, we're gonna stack as many as we can. And so we're gonna be checking A2 and CA. So the same thing as here, we're also gonna check if we can stack all of them. Let's first check if we can stack all. So if A2 is like bigger than or equal to CA, we can stack all of them onto the current weight. So this is easy, right? So just current, we're gonna remove it. I think it was yup, erase. I don't know if we can erase that right away though. I don't know how this works. So it just gives us key. So we can just say CW. And then we're gonna subtract. Right, we're gonna subtract the CA. So that's actually the easy case. Otherwise, we can only partly stack. And how many can we stack? Well, we can only stack how many whatever we have, because we can partly stack. So we only have A2. We can stack all of that. So we're just gonna say, oh, I can just say this, right? I can just refer to it. Okay, anyways, so we're CW. We're gonna refer back to this, and we're gonna just subtract it by A2 because we can only stack. Yeah, we can only stack how many ever we have. So we're gonna subtract by that. Then we also need to be tracking our total result. And our total result is gonna be here. Our total result, it's going, yeah, we need to keep track of total result. So every time we stack something, every time we do like basis, we need to keep track. So we subtract equal to m minus basis, we need a total plus equals. Okay, so, oh wait, what is? Okay, yeah. Okay. So this is where we stack all of them, so it doesn't really matter. So total plus equals a. So now we have our total. When we partly stack, when we stack all, we also need to update our total. So can't stack. A2 is bigger than or equal to. Okay, yeah. So now we can partly stack. We're trying to break now. So current CW minus A2. We've just stacked A2, so total. Total plus equals A2. Yup, so we subtracted from the thing. Erase CW. Okay. If you erase CW already, then why are you doing it? What did I do? Okay, so we're gonna put this down here. We're gonna add it first. Okay, so this is just stacking. I think this stacks everything. Yeah, all the leftovers just go to waste. So total. So if you can stack it, then you stack all of them. If you can partly stack, then you only then you only stack a little bit. But then you do break, and I think I should delete the equal sign over here, because if it's equal, then we're no, no, because if it's equal, we still need to erase it from the current. We do stack all of them, and then we should stop. Yeah, then we should always partly stack. I think we're good. Because if our A2 is equal to 0, next time we come here, even though we can stack, we're gonna have to partly stack, because 0 is never bigger than CA. So when we stack A2, we're just gonna do nothing. If it can't stack anymore, we're gonna break. Is there anything else we should do? I think this should be it. I will debug. I will need to debug. But I think this should just be it. Unless there's some other checks that we need to do, because I think we're lacking checks. 9. Is 9 the oh. I did not think we would actually ace on the first. Okay. I actually did not think we would ace it on the first one. That's actually insane. What about the first case? Okay, I think the first case is easier than the next one, because I think, yeah, just 5 5. You would just stack 5, and then you would stack 7. So, oh, segment fault out of nowhere. I have no idea. I have no idea what this is. So I think I'm gonna debug. I really don't know what this is. Should be the easiest one. Okay, so we're gonna go here. We're gonna say int w1 w2, and we're gonna do this. We're gonna add the bases, and then we're like, okay, we literally added all the bases. So then we go like here, then we go here, then we go here. Now we're gonna stack up. We stack the what? Oh, yeah, right. We're trying to stack it on the 5. So our current W should be, so we have 7 to 6 here. Yep, 7 6. But we got 6. That's like a lot. And so we can stack all of them. So we're gonna subtract by CA, which is 5. And we total axle, we're gonna remove segment fall. Okay, I think it's something about the removal going weird here. But yeah, it's definitely the removal. Yeah, and we never actually checked like how many we stacked. We actually didn't stack it, so we didn't add it to the next one. We need to do something to the removal. We need to do something to removal here. We cannot simply remove CW. We cannot, because then the whole for loop is weird. So I think the way to go is to remove it at the end. So here, vector, and remove is rem a thing? I don't think so. So remove. We're gonna push back CW because we don't like it. Now we need to keep track of the current total that we just stacked. So taught. And every time we add to the main total, we gotta add to the current total. So why not just replace it to the current total? Right, why not just do that? And oh no, not insert. Oh my god. Okay. So now we're gonna do the same thing here. I'm blanking on my Vim commands. Okay, so over here, current total. Awesome. So now we have our current total. Outside of here, we're gonna just do a little bit of job here. So total plus equals current total just means the number, just means the stuff that we stacked. Then we're gonna cycle through rem, and we're gonna remove our. I think this is good. So I'm gonna run it one more time just to see. But right now we're just storing it into a rem. We have the current total. We're gonna return total. Oh, we never actually added the current. Okay. We never actually added the current total to the end of the array. I mean the map. We need to do that. So unless current total, unless we haven't added anything, we need to put it in. So unless we haven't added anything, we're gonna have to put this current total in the map. So the current of whatever weight we're looking at here. So whatever weight we're looking at is as well as it's known as weight 2. We're gonna set that into the number of items that we added. Okay, one more time. This should be good. We just add it back. If it's not 0, that is 14. Awesome. 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 Just to like more, just to make sure more, let's actually do this case over here, because I think this case you can add all of them. I think 1, 2, 3, 4, 5, 6, 7, all but 1. Right. Yeah. Okay. So just hold on until I type out the whole thing. Okay, so now I've typed everything out into the input. I'm just double checking to make sure this actually makes sense. We have 7. Yeah, I think it makes sense. So let's run this and hope that we get our answer, which is like, well, sometimes 3 is just 21. So I think 20. Yep. Okay. So according to my logic, this code is good and working. Maybe according to the other test cases that we're about to see, it's not what it is, but we're gonna submit it anyways, and then we're gonna try to find our error. Okay. Okay, let's see. Oh, okay, our logic was good, and okay, so it didn't time out. I'm actually happy about that. There's just one more thing, and it's the yeah, it's not so good. So from 13 to 17 we got everything wrong, and inputs 12 to 17 has no additional constraints. So the first thing I want to check is lone wolf. We have a lot of 10-9s here. I don't want to be adding stuff, right? I don't want to be adding stuff and exceeding the limit. We have a bunch of weights. We have a bunch of stuff. Oh, so the only thing that we're adding is the total. So if I change the total, will I be able to pass the case? Because is the total gonna be more than, yeah, I think we can stack like a lot of stuff. So let's define the long first. Pretty sure this works. And in total here, we're just gonna do that. So unless that's the only long one that we need to do, so we're just adding right here. That's the only thing we're adding. The current total is also gonna be affected. Current total is also kind of like adding. So we're gonna add long to that. Then yep. Alright, hopefully now that we've added the long, it actually works now. Please. Okay. 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 Oh my god. Yes. First life solve is actually went well. Um, you guys don't know how happy I am. Even though I've already passed silver, the problems are definitely getting harder and harder. I mean, for this problem, I was not sure how to do it, and oh my god, oh my god. Okay, okay. The problems are definitely getting harder. For so for this problem, the analysis was, the analysis was like, I guess it wasn't super hard, but it was like medium level. I mean, the first solution that I came up with of just like stacking everything like normally, that's definitely not gonna work. So and then I thought about like simplifying this solution, making like just doing everything at once, because in theory, if we're just stacking stuff on top, we might as well just make everything first and then stack stuff on top. Like instead of doing it one by one. I don't know how I came up with that. But I did. And so obviously this is like you have to keep track of it using a map here. And I think C++, it really helped me out there because it automatically stores stuff in a map so that every time I cycle through it, it's already sorted. I really like that because in Java and like other languages, you can't really do that. So, wow. Okay, so definitely the live solves are different from the normal explanations. I actually feel the intensity and uh the amount of excitement that I get just by submitting each code here. But we've done it. We've done the live solve, and I think in a pretty good time. I think it's just like, yeah, we didn't take forever on it, so that's good. Thank you guys for watching. If you guys want me to do these kind of live solves more, and I think uh, some of these live solves won't go as well as this, but if you guys want to see more of this, please click subscribe and like, and also comment and which problem you want to see me do next, which problem you're still confused about, and I'll maybe do a live solve on it, or I'll maybe do a normal solve if I've already solved it before. Again, thank you guys for watching, and I'll see you in the next USACO problem. And I forgot the date.